this video, we're going to go over velocity and acceleration. All right, let's begin. So, as a reminder, here are the definitions. We're going to be going back and forth between these definitions. So definitely pause the video and listen to me explain this after you copy everything down. So, velocity, the definition of velocity actually has a formula within it. You can think of velocity as the idea of speed, or how fast or how slow something is going. But the important thing that I want to point out is that the biggest difference between velocity and speed is that velocity is a vector. So the direction matters for the communication purposes, compared to speed, where direction doesn't matter. Now, the thing that I like to tell students is that your cars have a speedometer, right? So right behind your wheel, you can see how fast you're going, right? So that's a speedometer, which tells you how much speed you have at that moment. And it's not a velocimeter, because that meter doesn't tell you what direction you're going. Okay, so speed and velocity almost identical, except velocity cares about direction. Okay, the other big difference between the two is that velocity uh, is looking at displacement, okay, versus speed, which looks at distance. Now, it's important to point out here that displacement is, in fact, a vector, and distance is a scalar. So the two correlate with each other. All right, cool. So acceleration is how much your velocity is changing. Now, in your car, you actually have two pedals that can change, or that can accelerate your car. You have the gas pedal, which makes you go faster, and you have the brakes, which makes you go slower. But both of those pedals changes your velocity. It changes your speed. All right. Variables, units, and formulas. So let's start off with velocity. Okay. But before we go into velocity, so a quick reminder of some symbols. This triangle is delta. In delta, you're looking at final minus your initial. Okay. And x is position. Okay. And the reason why we bring that up is because delta x is the change in position, which we call displacement. All right, so displacement, the units are m, as in meters. Now let's go into the new stuff. Velocity. Velocity is a vector, so you'll often see me have that little arrow on top. Velocity is the change in position over a measure of time. Now, sometimes you'll see me put a little triangle there because there has to be a change of time. Sometimes you might not see me do that, but just so you know, that is over a unit of time. So we can extend this formula a little bit further. So we get xf over xo all over t. And the units are meters per second. Okay, so one more time, velocity, this is the variable. Right here is your formula. And right next to it, those are, of course, our units. All right, so the units tell us a lot about the variable itself. It's how much or how many meters that we're traveling for every second. Okay, so it's a ratio. All right, now let's do speed. Speed, because it's a scalar, we don't need that arrow. Speed is just total distance over time. All right, and the last one is acceleration. So let's do a quick reminder of the definition of acceleration. Remember, acceleration is how much your velocity is changing. Okay, and so therefore our formula fits that. Acceleration is a change of velocity, and velocity is a vector. So acceleration is also a vector. It's delta v over t, or v final minus v initial all over time. Okay, and I'm going to show you two ways of writing the units for acceleration. You'll see one more frequently than the others, but so that one is meters per second squared. okay, you'll see that one written commonly, meters per second squared. However, as we get used to the idea of acceleration, we can go more towards this. But a better way of thinking acceleration is, once again, a ratio, is how much your velocity, or meters per second, is changing for every unit of time, seconds. Okay, so how much your velocity is changing for every unit of time, seconds. So you'll often hear me at the beginning of the year have the units for acceleration as meters per second instead of meters per second squared. It's just a better way of understanding what acceleration truly is. It's a change of velocity per unit of time. Okay, so let's go into the vector explanation of velocity and acceleration. So the first model I want to show us, this is called the constant velocity model. Meaning, I'm going to represent an object's position as dots. So let's say we have an object there at time of 0 seconds, and the object goes here at 1 second, 2 seconds, 3 seconds, 4 seconds. Right? So there's a total of 4 seconds. And just so that we remember, this is 0, and this right here is 4 seconds. Okay, so if we look at the formula for velocity, it's the change in position over a unit of time. So let's say at every second we travel 2 meters. So from here to here, this is 2 meters, and from here to here, it's 2 meters. So what this shows us is that for every second, we're traveling the same amount of distance. Okay, so for every 2 meters, we will travel for every 1 second, we travel 2 meters. Okay, so what this tells us that the velocity is 2 meters per second. Gives us a ratio. And the reason why I'm saying it's a ratio is even though this 2 is a whole number, technically there's a 1 in front of this seconds unit, so it's 2 over 1. Okay? Now in terms of vectors, okay, because we are going to be utilizing the tip-to-tail method here in a little bit, if I were to draw the velocity vector, okay, this object would have a velocity vector that looks like this. Like this. Like this. Okay, and I tried my best here, and I hope you can see that I tried to make all those velocity vectors the same size. All right, so this velocity vector is all the same. We have the same constant velocity. Now let's compare that to the accelerated model, okay, or the constant acceleration model. All right, so we're going to go with the same idea, where we're accelerating by the same amount. Now, as a quick reminder, there's a reason why I'm reminding us of this many times, because it's a very common misconception that acceleration is actually describing motion, but it's not describing motion. Motion is velocity. Acceleration describes the change of motion, how much your movement is changing. So let's do a couple of dots. Here we have dot 1 at 0 seconds, dot 2 at 1 second, and watch what I do here, okay? I'm spacing out the position of the objects, so 0, 1, 2, 3, 4, all right? So what this is showing us is that the object is getting faster and faster, and we know that because if we draw the velocity vector, okay, so the first velocity vector looks like this, and then you can see that my velocity is in fact increasing. Like so. So we can see that my velocity is increasing, which means that the object is getting faster. So to represent this with acceleration, remember acceleration is the change of velocity. Let's say that we get this first vector, okay, and we compare it with the second vector right there. Okay, so we're comparing those two vectors. So if I were to draw the first vector right underneath of it, remember, acceleration is a change in velocity. So I'm going to show you, and let's do this in red. The difference between this top vector and this bottom vector is this arrow. So this red arrow right here, this is your acceleration. That's how much your velocity changed, okay, from your initial velocity to your final velocity. If this is v initial, and this here is v final, okay, this red here is how much the velocity has changed. right? And if we have constant acceleration, then what that means is if I were to take the same arrow, right? So if we take this arrow right here and redraw it right underneath, okay, I'll try to draw the same length, we can see that the difference between the two is relatively the same acceleration arrow. I'm going to try that again. I'm going to take this arrow and compare it to this arrow. I want you to look at that. My acceleration across all time points, we have the same acceleration, which just tells us that our acceleration is changing by the same amount. So, that's what it looks like in terms of vectors, but, it's going to be a little bit easier if we associate numbers with it. So let's say that at time of 0 seconds, your velocity is, let's say, 1 meters per second, okay? And at time 1 second, let's say our new velocity is 3 meters per second. Okay, and so we can take a look here. The difference, okay, how much did we change our velocity by? I would say that would be 2 meters per second. So because this is a span of 1 second, and this right here, this is a change in velocity. And remember, the formula for acceleration is how much your velocity changes in a specific amount of time. We can say our velocity of change by 2 meters per second for every 1 second. So acceleration is 2 meters per second. Okay, so let's continue this trend. From 1 second to 2 seconds, 1 second passes by, and if acceleration is 2 meters per second, that means our new velocity is 5 meters per second. And let's just do that for prosperity one more time. At 3 seconds, our velocity would be 7 meters per second. So if I were to compare our initial velocity of 1 meters per second to our final velocity of 7 meters per second, we can say that our object did in fact speed up at a rate of 2 meters per second for every second. So that's the idea behind acceleration. Acceleration does not tell you the motion of the object, because that's velocity. Acceleration just tells you how much that motion is changing. All right? Okay. Now, with that, let's go into a different definition here. We're going to add to the definition of velocity, and we're going to add average velocity. So average velocity is the displacement of an object divided by the time in which the displacement occurs. Okay. So what this tells us is that we only care about the traveling, the shortest distance between your start and your finish. The path doesn't matter. Meaning, so this is a callback back to displacement. If we started here, okay, at time, let's say 0 seconds, and we ended here at time is of 2 seconds, right? We could have just walked in a straight line like so and go from start to finish, which is the shortest path, which is displacement, or we could have taken, this long loopy way to get there. Now, this one, we have a greater distance, okay, but both of them have the same displacement. All right, average acceleration is the velocity of an object divided by time in which the change occurs. Okay, and so we're going to take a look at both examples here in the next slide. Okay, so let's try this problem out. I encourage you to sketch this along with me and try to solve it yourself. Okay, so we have a car and it starts at the -3 meter mark. So now what I'm going to do is I'm going to create a little number line of some sorts. We're going to say this is the origin, okay, ORIGIN. This just tells us that that's the 0 meter mark, but we don't start there. We actually start over here at the -3 meter mark, okay, at time of 0 seconds. And from there, we go all the way out, okay, all the way out to the 12 meter mark. So let's draw that one right there. So right there, this is 12 meter mark, and it took us a total of 4 seconds. And then from there, we travel back to the 1 meter mark. Yeah, right there. If you're wondering, it's really your color system doesn't make any sense. I'm sorry. And that took a total of 2 seconds. So from here to here is 4 seconds, and from here to here is 2 seconds. So we are looking at a total of 6 seconds when we reach the 1 meter mark. All right, let's do total distance traveled. So remember, distance is a summation. So we go from -3 to 12. So that would be 15 meters that we travel in the first leg, and then from 12 meters to 1 meter, so that would be 11 meters. And so this is 26 meters of your total distance traveled. All right, displacement. Displacement, we can actually see it if we use the tip to tail method, right? We go from the very, very start, which is right here, and we draw an arrow to the end, which is right there. So this right there, our purple arrow, is your displacement. But let's use the formula, okay, to figure it out. So displacement is final position minus your initial position. And we know our final position is 1 meter, and our initial position was -3 meters. And see what I did there? I did minus -3, okay, because we gotta substitute in the formula correctly. And so 1 minus -3, we get a total of 4 meters. So the object was 4 meters to the right is your displacement. Okay, now that we have all that, let's try to figure out the average velocity. Okay, so the average velocity, if you remember the formula, V average is your displacement over a period of time. And so if we're going to figure out our displacement, it's 4 meters to the right, okay? And the total time that it took, so from here to here is 4 seconds, from here to here is 6 seconds, so a total of 6 seconds. So 4 divided by 6 would be, what is that? 0.67 repeating meters per second to the right. That would be your average velocity. And if we take a look at your speed, okay, so speed's a little bit different. Speed is your total distance divided by the total time. The total time is still 6 seconds, and the distance we figured it out to be 26 meters. And if we plug that into the calculator real quick, we get, there we go, 4.33 meters per second. So we can see that in order to make this convoluted travel, we had to go pretty fast, or we could have taken our time nice and slow and just travel this displacement right there, and then we would have gotten to the same spot. All right, so that's our example. A function, okay, so sometimes you'll be given a function and you'll be asked to find different things about it. In this case, I'm going to ask you to find the average velocity. So this function describes a object's motion or the object's position with respect to time. So we are going to do, let's take a look at from 1 second to, say, 3 seconds. Okay, what is the car's average velocity between these 2 points in time? So let's do the 1 second one first. What I'm going to do is I'm going to substitute in the 1 into the function, and what we get is at 1 second, the object is at 5 meters. Okay, and we're going to do the same with the 3 seconds. So now I've got to be a little bit careful here with my algebra. So 9 times 2 is 18, so 21. There we go, 21 meters. And at 3 seconds, the object is at position 21 meters. So we found, where we're about to find the displacement. So remember, displacement is final minus initial position. Our final position is 21 meters. Our initial position was 5 meters. So our total displacement would be positive 16 meters. And the time that it took, the delta t, okay, we went from 3 seconds to 1 second, so it will be 2 seconds. Now, this is all the necessary information for the average. So remember, the average velocity, you're looking at the displacement over the change in time. In this case, it was 2 seconds. So displacement was 16 meters over 2 seconds. So that gives us a velocity of positive 8 meters per second. All right, and that's that. I'll see you in the next video. We're going to look at the same function, but we're going to analyze it graphically.